summer 1940, and Britain confronted a nightmare unfolding in darkness. Every night, German fast attack craft raced across the narrow waters separating occupied France from English shores, striking merchant convoys with devastating precision. These enemy vessels, called E-boats by the British, moved like ghosts through the Channel darkness, launching torpedoes before vanishing into the night. Traditional British destroyers arrived too late, their quarry long gone before these massive warships could close the distance. The Royal Navy possessed magnificent vessels bristling with guns and armour, ships that had ruled the waves for centuries. But for this specific battle, they had precisely the wrong equipment. Consider the mathematics of the problem. A fleet destroyer cost approximately £500,000 to construct during this period. Each required specialised naval dockyards with enormous slipways, precision engineering facilities, and 18 months of construction time using highly skilled labour trained to exacting standards. These destroyers displaced nearly 1,700 tons, drew too much water for shallow coastal operations, and represented far too valuable an investment to risk in mine-infested waters hunting nimble opponents. Their operational costs extended far beyond construction. Maintenance demanded specialised facilities. Repairs after combat damage consumed months and enormous resources. Crews of 200 men required training, feeding, housing. Every destroyer committed to coastal patrol was a destroyer unavailable for Atlantic convoy, escort, fleet operations, or surface combat against capital ships. The Admiralty needed something entirely different. Not bigger weapons or heavier armour, but numerous expendable vessels capable of matching E-boat speed and operating in shallow waters where destroyers couldn't venture. They needed boats that ordinary boatyards could build quickly using available materials. They needed vessels that could be lost without catastrophic strategic impact, that could be replaced within weeks rather than years, that required small crews rather than hundreds of trained sailors. Most critically, they needed enough of these boats to establish numerical superiority, to patrol continuously, to make coastal waters too dangerous for enemy operations. The solution emerged from an unexpected quarter. Motor torpedo boats constructed from plywood and powered by automobile engines adapted for marine use. These craft cost roughly £30,000 each, approximately 1/16 the price of a destroyer. Small boatyards that normally built pleasure yachts could produce them in weeks rather than months. They carried crews of 12 instead of 200, measured 70 to 73 feet long instead of 360, and displaced 33 tons instead of 1,700. Critics immediately dismissed them as toys unsuitable for serious warfare. Traditional naval officers argued plywood couldn't withstand combat, that wooden hulls would splinter under shell fire, that petrol engines created unacceptable fire hazards. Every objection was perfectly valid. None of it changed the fundamental calculation. By war's end, British coastal forces operating these fragile wooden boats had destroyed approximately 400 enemy vessels while losing 170 of their own craft. The tonnage destroyed ran into millions. 48 E-boats were sunk, eliminating the German advantage in coastal warfare. German coastal convoys required destroyer escorts specifically to defend against MTB attacks, pulling valuable warships from more critical duties. The D-Day invasion proceeded under MTB protection that prevented German discovery of the assembling fleet. This is how Britain won the coastal war with materials furniture makers understood better than admirals. The strategic problem stemmed from geography that favoured the attacker. The English Channel, barely 20 miles wide at Dover, had become a killing ground after France fell in May 1940. German forces controlled the entire coast from Cherbourg to Calais, providing perfect staging areas for fast attack operations. E-boats based in French and Belgian ports could reach British convoy routes in under an hour, attack from multiple directions, then return to base before dawn. These German vessels were formidable opponents. They displaced nearly 100 tons, substantially larger than early British MTBs. They featured diesel engines providing remarkable range and eliminating the fire hazards of petrol. Their hulls incorporated more robust construction than British designs with steel frames and planking that could absorb more punishment. The E-boats carried two 21-inch torpedoes and substantial gun armament, including 20mm cannons and machine guns. Their crews were highly trained specialists who had perfected night attack techniques. Most critically, they operated from bases so close to British shipping lanes that interception became nearly impossible using conventional naval assets. An E-boat could sortie from Cherbourg, strike a convoy off Portland, and return to base in under 4 hours. British destroyers based in Portsmouth or Plymouth couldn't respond quickly enough to intercept them. Even when destroyers did engage, the E-boats simply outran them, disappearing into darkness at speeds exceeding 40 knots while destroyers struggled to maintain 36. British destroyers faced insurmountable tactical disadvantages in this environment. Their maximum speed of 36 knots couldn't match E-boat performance. Their deep draft of 12 feet or more prevented operations in shallow waters where E-boats maneuvered freely in 6 feet of water. Their radar signatures made them visible to enemy coastal watchers long before they could surprise their quarry. Their size made them easy targets for coastal batteries protecting E-boat bases. Most fundamentally, Britain couldn't afford to deploy expensive destroyers on coastal patrol when they were desperately needed for Atlantic convoy escort, fleet operations, and dozens of other critical missions. Every destroyer committed to Channel patrol was a destroyer unavailable for protecting merchant convoys, bringing vital supplies from America. The strategic requirement was clear. Britain needed vessels that could patrol continuously in coastal waters, engage E-boats on equal terms, intercept them before they reached convoys, and be replaced quickly when lost. This mission demanded hundreds of small craft, not dozens of large ones. It demanded vessels that could be risked without hesitation, that could operate in minefields and under coastal artillery fire, that could be built using resources not required for more critical programs. Traditional naval thinking offered no solution. Coastal defense had never been a Royal Navy priority. The fleet existed to control oceans, not defend shorelines, but the war had changed calculations. Without coastal control, convoys couldn't reach port safely. Without safe ports, Britain would starve. The man who understood this requirement before the Admiralty accepted it was Commander Peter Dunckirk, managing director of Vosper Limited. His company specialized in high-speed motor yachts for wealthy clients, employing techniques that prioritized speed over strength, planing hulls over displacement designs. Dunckirk had studied fast boat design extensively, understanding how lightweight construction and powerful engines could achieve speeds impossible for conventional vessels. His yachts regularly won races, demonstrating capabilities that impressed naval observers even if they didn't immediately recognize military applications. In 1936, Dunckirk committed company funds to developing a private venture motor torpedo boat, gambling that war was inevitable and that Britain's coastal defense would eventually require exactly what he was designing. The gamble cost Vosper approximately £25,000, money a medium-sized boatyard could ill afford to waste on speculative projects. Dunckirk proceeded anyway, convinced that traditional naval procurement moved too slowly to prepare for the coming conflict. He had watched the Admiralty reject proposals, demand modifications, form committees to study requirements. By the time official procurement programs began, war might already be underway. Better to build the prototype first, demonstrate capabilities, then sell the concept. If the Admiralty refused to buy, at least the boat could be sold to foreign navies or converted for commercial use. The risk was substantial, but Dunckirk believed the need was obvious to anyone studying European politics and German rearmament. The prototype, designated MTB 102, emerged from Vosper's yard in 1937. Her construction showcased techniques borrowed directly from yacht building rather than naval architecture. The hull used double-diagonal mahogany planking over rock elm frames, layers of wood glued and copper riveted together to create a lightweight but rigid structure. No steel hull, no armor plate, just timber and 43,000 copper fastenings holding everything together. The construction technique was centuries old, perfected by generations of boat builders for fishing vessels and pleasure craft. What made it innovative was the application to military purposes, the realization that speed and numbers could substitute for armor and individual survivability. 3 Isotta Fraschini engines generating 3,300 horsepower drove her to 48 knots when running light, 43 knots, fully loaded with torpedoes, fuel and crew. These Italian engines were marvels of engineering, powerful and reliable when properly maintained. They gave MTB 102 performance that shocked Admiralty observers, accustomed to destroyers that struggled to exceed 30 knots. She measured 70 feet long, displaced 33 tons, and required a crew of just 12 men, including officers. Two 21-inch torpedo tubes provided offensive armament capable of sinking any merchant vessel or damaging major warships. Machine guns offered defensive capability against aircraft and other small craft. Essentially, Dunkirk had created a racing yacht capable of sinking cargo vessels, a speedboat that could deliver the same torpedo punch as a submarine or destroyer, but at a fraction of the cost and with far greater speed. The Admiralty tested MTB 102 extensively throughout 1937 and into 1938. The boat exceeded specifications, demonstrating both remarkable speed and adequate seaworthiness for coastal operations. She could maintain high speed in moderate seas, maneuver quickly, launch torpedoes accurately. Her wooden hull proved more resilient than expected, flexing with wave impact rather than cracking like steel. Her engines, while demanding careful maintenance, delivered consistent power, but recognition didn't translate into immediate production orders. Naval traditionalists raised numerous objections that reflected genuine concerns about unconventional designs. The wooden hull couldn't survive sustained combat. Even a single shell hit would penetrate, potentially causing catastrophic damage. The planing hull design limited operations to relatively calm seas. In heavy weather, MTBs would be forced to reduce speed or risk structural damage. Petrol engines created catastrophic fire risks when damaged by enemy gunfire. High-octane fuel would ignite instantly if shells penetrated tanks. The lightweight construction meant any shell impact would prove devastating. There was no armor protection for crew or machinery. Destroyers could absorb considerable punishment and continue fighting, could survive torpedo hits if properly compartmentalized. These plywood boats would disintegrate under fire, would sink rapidly if holed, would burn catastrophically if fuel tanks were hit. Every criticism reflected legitimate concerns. MTB hulls were vulnerable to damage in ways steel warships weren't. Heavy seas could break them apart if they operated beyond their design limitations. Engine fires could consume them in minutes once started. A single shell through the hull could sink them rapidly if it struck below the waterline. But the critics missed the essential point that Dunkirk understood instinctively. These boats weren't intended to replace destroyers or fight surface battles against armoured opponents. They were designed for hit-and-run attacks, for ambush tactics, for operations where speed and surprise mattered more than individual survivability. The true test wasn't whether an MTB could survive damage, but whether Britain could afford to build enough of them to control coastal waters through numerical superiority. May 1940 transformed debate into urgent action. France collapsed under German assault, creating a catastrophe that changed every strategic calculation. Germany seized the entire Channel coast from Belgium to Brittany, gaining bases within minutes of British shores. E-boats began their nightly campaign of destruction immediately, sinking merchant vessels within sight of English beaches. Suddenly, questions about MTB suitability became irrelevant. The Admiralty needed coastal defence vessels immediately, and conventional destroyers couldn't fill that role economically or numerically. Orders flooded to Vosper, British Powerboat Company and Thornycroft. Not dozens of boats, but hundreds. The specifications were deliberately simple to accelerate production and allow maximum flexibility in construction methods. 70 to 73 feet long, wooden construction using mahogany planking over elm or oak frames, 2 torpedo tubes mounting 21-inch weapons, machine guns for defense against aircraft and small craft. Any competent boatyard familiar with wooden construction could build them using techniques already mastered for commercial vessels. This proved transformative for British industrial capacity. Destroyer construction required specialized facilities found only in major naval dockyards. Britain possessed perhaps 7 shipyards capable of building destroyers to military specifications, each with limited capacity and lengthy production schedules. Every destroyer built consumed resources needed for other programs. Every destroyer under construction occupied a slipway for 18 months or more. MTB construction required none of this infrastructure. Vosper's main facility sat in Portsmouth Harbour alongside yacht builders and furniture manufacturers who worked with wood daily. When production accelerated dramatically, contracts went to companies with no military experience whatsoever. Camper and Nicholson built racing yachts for wealthy sportsmen. John Mees specialised in motor launches for commercial and pleasure use. Thornycroft produced small craft. Whites of Cows catered to yacht owners. These companies understood wooden hull construction intimately, having perfected these techniques over decades building pleasure craft. They employed craftsmen skilled in working mahogany and oak, in bending frames and planking hulls, in riveting and gluing joints. All these skills transferred directly to MTB construction with minimal adaptation. The material requirements made mass production economically feasible in ways destroyer construction never could. Destroyers demanded specialized naval-grade steel produced in limited quantities by specific foundries. They required precision turbine components manufactured to exacting tolerances in dedicated facilities. They needed electrical systems built to military specifications. Every component involved long supply chains, specialized manufacturers, critical materials in Puckham, limited supply. MTBs used commercial-grade mahogany from Honduras, rock elm from Canada, and standard plywood from ordinary timber mills producing material for civilian construction. The wood could be sourced from multiple suppliers, didn't require specialized facilities, could be stockpiled easily. The engines were Packard 512 units, V12 marine engines originally designed for luxury automobiles and adapted for boat use through relatively simple modifications. Packard produced these engines in quantity for civilian markets, making them available without competing for limited military manufacturing capacity. When Packard production couldn't meet accelerating demand, British yards installed whatever powerful engines they could obtain. Aircraft engines were modified for marine use. Truck engines were adapted. Even captured Italian engines found their way into MTBs when nothing else was available. This flexibility in material sourcing meant production wasn't constrained by specialized military supply chains or dependent on limited suppliers who might be bombed or whose production might be needed for other programs. Construction speed reflected these fundamental differences in complexity and industrial requirements. At Vosper's Portsmouth works, an MTB hull took shape in open sheds using yacht-building techniques refined over generations. Craftsmen laid diagonal mahogany planking over bent elm frames in sequences that created strength through multiple layers oriented in different directions. Each layer was glued with marine adhesive and copper riveted to frames and adjacent planking. The process was labor-intensive but didn't require specialized equipment beyond basic woodworking tools. 20 skilled woodworkers could complete a hull in 6 weeks of steady work. The hull could be built outdoors under temporary shelter, didn't need heated facilities, could proceed in almost any weather. Installation of engines, torpedoes, guns, and equipment required. Another month. Engines were mounted on bearers, connected to propeller shafts through flexible couplings. Fuel tanks were installed and plumbed. Torpedo tubes were mounted and tested. Guns were installed with ammunition storage. Electronics and navigation equipment were fitted. Each MTB emerged as a complete fighting vessel ready for sea trials and crew training. Total construction time from keel laying to commissioning was 8 to 10 weeks under normal conditions. Under pressure, this could be reduced to 6 weeks for hull construction plus 3 weeks for fitting out, 9 weeks from start to operational capability. Compare this to HMS Javelin, a J-class destroyer laid down at John Brown Shipyard in Clydebank, Scotland, in October 1937. Her construction required precision-matched turbine components manufactured across multiple facilities by specialist companies. Each turbine had to be balanced to fine tolerances, blades precisely machined, bearings manufactured to exact specifications. Her boilers required specialized steel fabrication, pressure vessel certification, complex piping systems. Her electrical systems were custom designed for naval specifications, with generators, distribution panels, lighting systems, communication equipment, all built specifically for destroyers. Fire control equipment was built to tolerances measured in thousandths of an inch, with mechanical computers to calculate firing solutions, optical rangefinders precisely aligned, gun mountings carefully balanced. She commissioned in June 1939, 21 months after construction began, representing approximately 400,000 man-hours of highly skilled specialized labor. Workers included precision machinists, specialized welders, electrical engineers, pipe fitters, all trained to naval standards. Javelin was unquestionably superior in every measurable category. She displaced 1,700 tons versus an MTB's 33. Her 6.4, 0.7-inch guns in 3 twin turrets vastly outgunned an MTB's machine gun armament. Her steam turbines generated 40,000 horsepower compared to an MTB's 3,300, driving her to 36 knots. She could operate in any weather conditions from calm seas to hurricanes. She could cross oceans, fight surface battles against comparable vessels, provide anti-aircraft protection for convoys, bombard shore targets. She was a complete warship capable of independent operations worldwide. She was also a single ship that consumed 21 months of construction time and £500,000. In those same 21 months, British yards completed approximately 90 MTBs using labour distributed across dozens of small boatyards rather than concentrated in specialised naval facilities. Those 90 MTBs represented nearly £3 million of investment, but they also represented 90 separate units that could patrol 90 different locations. Simultaneously, that could be risked in dangerous waters, that could be replaced individually when lost. Javelin was irreplaceable in practical terms. Building a replacement would consume another 21 months and another £500,000. Losing Javelin meant losing years of construction effort and enormous resources. The cost differential was staggering and strategically significant beyond simple arithmetic. A destroyer consumed approximately £500,000 in 1940 currency. An MTB cost roughly £30,000. That 17-to-1 cost ratio fundamentally altered strategic calculations at every level. For the price of one destroyer, Britain could deploy 17 MTBs to 17 different patrol areas. For the construction resources required to build 3 destroyers over 5 years, boatyards could launch more than 50 MTBs in 18 months. The cheap plywood boats weren't replacing destroyers in any functional sense. They were filling operational requirements. Destroyers couldn't address economically regardless of their superior individual capabilities. Destroyers were absolutely essential for ocean convoy escort protecting merchant ships crossing the Atlantic. They were critical for fleet operations supporting battleships and carriers. They were needed for surface combat against enemy destroyers and cruisers. Every destroyer represented a strategic asset that couldn't be risked in coastal waters or committed to missions that smaller vessels could perform. MTBs could handle the coastal mission economically, could be built without consuming resources needed for destroyers, could be lost without strategic disaster. The mathematics favoured this division of labour overwhelmingly once analysed objectively rather than through traditional naval thinking that prized individual ship capabilities over strategic flexibility. But cost-effectiveness meant nothing if the vessels couldn't fight effectively. MTBs had to prove themselves operationally against real enemies under actual combat conditions. The first tests came immediately in the desperate spring of 1940. MTB 102, the prototype that critics had dismissed as unsuitable for military service, participated in Operation Dynamo, the evacuation of British and French forces from Dunkirk. She crossed the Channel 8 times under constant air attack, carrying soldiers from beaches and harbour, serving as flagship for Rear Admiral Frederick Wake Walker after his destroyer HMS Keith was sunk by German bombers. The plywood boat survived what the steel destroyer couldn't, demonstrating that speed and manoeuvrability could substitute for armour when properly employed. Tactical doctrine developed rapidly through these combat experiences and the lessons of early operations. MTBs operated in flotillas of 6 to 8 boats, hunting at night when their low profiles made them nearly invisible against dark water. The boats were painted dark grey or black to reduce visibility further. They approached targets slowly on auxiliary engines to minimize noise and avoid creating visible wakes that might alert lookouts. This patient approach required nerve, creeping toward enemy vessels at 5 or 6 knots while vulnerable to discovery. But once in position, they unleashed full power for the final attack run. The transition from slow approach to high-speed attack was critical to survival. MTBs accelerated to 40 knots, closing rapidly from positions where enemy gunners couldn't track them effectively. They fired torpedoes at point-blank range, typically 300 to 500 yards where accuracy was nearly guaranteed. At these ranges, torpedo running time was measured in seconds. Enemy vessels had virtually no time to take evasive action. Then the MTBs disappeared behind smoke screens, changing course radically while obscured, running at maximum speed on unpredictable headings. The tactics were brutally simple in concept but demanding in execution. Approach undetected using darkness, patience, and careful seamanship. Fire torpedoes at point-blank range where missing was nearly impossible. Escape at maximum speed using smoke and radical maneuvers. The success of these tactics depended on specific characteristics that MTBs possessed but destroyers lacked. Small size made them difficult to spot visually, especially at night. Low profile meant they disappeared against dark water beyond a few hundred yards. High speed meant they could close rapidly or escape before enemy gunners could establish accurate fire. Maneuverability meant they could change course instantly, could dodge between ships in convoys, could navigate through minefields and shallow waters. These capabilities combined to create a platform optimized for coastal ambush warfare, even though individually fragile. The weapons made these tactics viable beyond simple hit-and-run attacks. 21-inch torpedoes carried 700, 50-pound warheads capable of breaking a merchant vessel's back or inflicting catastrophic damage on any warship short of a battleship. MTBs typically carried 2 torpedoes, though later variants mounted 4. The torpedoes were expensive weapons, each costing thousands of pounds, but they transformed a 30,000-pound boat into a platform capable of sinking millions of pounds worth of enemy shipping. This force multiplication made MTBs economically efficient beyond their construction cost. The boats also evolved to carry depth charges for anti-submarine operations, attacking U-boats on the surface at night. Oerlikon 20mm cannons provided firepower for surface combat against E-boats and smaller craft. Multiple machine guns offered defense against aircraft, could suppress enemy gun crews during attacks, could be used for strafing shore targets. MTBs evolved from pure torpedo boats into versatile platforms capable of multiple missions. This versatility proved crucial operationally. Coastal forces missions varied dramatically night by night. One patrol might involve torpedoing a German convoy moving supplies along occupied coasts. The next could mean escorting commandos to a beach for a raid. The following night might require intercepting E-boats before they reached British convoys, laying mines in enemy harbours, rescuing downed airmen. The missions multiplied and MTBs adapted to all of them. The human element proved equally critical to operational success. MTB crews were volunteers who chose this dangerous service over safer assignments. They were typically young officers barely out of training, sub-lieutenants and lieutenants in their early 20s, and ratings who preferred action over routine assignments aboard larger vessels. They operated under conditions that would have destroyed morale on conventional warships. The boats rolled violently in any sea state above flat calm. The wooden hulls amplified every wave impact, transmitting shocks through the structure that made sleep difficult and comfort impossible. Crews stood watches on open bridges exposed to channel weather, rain, spray and winter cold that penetrated every layer of clothing. Petrol fumes permeated every space below deck. The boats carried up to 5,200 gallons of high-octane fuel in tanks surrounding the crew compartments and engine room. These fumes created constant headaches, nausea, and the knowledge that any spark could trigger catastrophic fire. Engine noise was deafening when running at high speed, making communication difficult and sleep impossible for off-watch crew. Accommodation was minimal. Bunks were narrow wooden shelves with thin mattresses. Cooking facilities consisted of a small stove. Toilet facilities were primitive. Storage space was insufficient for food, spare parts, ammunition, and personal gear. Yet these young men performed brilliantly night after night, demonstrating remarkable courage operating fragile vessels against well-armed opponents in confined waters. Their average age was 21. Many had never commanded anything before receiving an MTB. They learned navigation, ship handling, tactics, leadership under combat conditions with little margin for error. Their casualty rates reflected the dangerous nature of the service. Approximately 1,400 officers and ratings of coastal forces died during the war. Boats were sunk by E-boat gunfire, destroyed by mines, lost to accidents in bad weather, caught by destroyers and blown apart. But survivors returned to duty, trained new crews, refined tactics based on hard experience. MTB flotillas based at Dover, Felixstowe, Portsmouth, Gosport and other coastal stations hunted nightly through 1941, 1942 and 1943. They intercepted E-boat formations before they could reach convoys, engaging in close-range gun battles in darkness where speed and aggression determined outcomes. They attacked German coastal convoys, moving supplies along occupied coasts from Belgium through France, sinking merchant vessels carrying ammunition, fuel, reinforcements. They laid mines in enemy harbours, dropping these weapons in shipping channels where German vessels would hit them. They supported commando raids, delivering troops to beaches and extracting them under fire, providing suppressive gunfire during landings. They rescued downed airmen floating in channel waters, saving pilots who would fly again. They performed reconnaissance missions, observing enemy ports and reporting ship movements. The operations were extraordinarily dangerous with casualty rates that would be unacceptable in most military units. But the mathematics consistently favoured Britain through replacement economics. When MTB 238 was sunk by E-boat gunfire in October 1942, Britain lost £30,000 and a crew of 12. The loss was tragic for the men involved, but strategically manageable. 7 weeks later, Vosper launched MTB 380 to replace her. The entire cycle from loss to replacement commissioning took less time than repairing minor damage to a destroyer. This economic resilience mattered enormously in attritional warfare where both sides suffered losses continuously. Between 1940 and 1945, coastal forces lost approximately 187 motor torpedo boats to enemy action, accidents, and weather. These losses represented tragedy for crews but remained operationally sustainable. Replacing them cost roughly £6 million total, money that could be found within naval budgets without crisis. Replacing 187 destroyers would have consumed nearly £100 million, a sum impossible to allocate. More importantly, replacing that many destroyers would have monopolised British shipyards for years, diverting construction capacity from other critical programmes. Each destroyer replacement would have meant fewer merchant ships built, fewer escorts for convoys, less capacity for new designs. Britain didn't have 187 destroyers to lose. The entire Royal Navy operated approximately 200 destroyers total throughout the war, split between Atlantic convoy escort, Mediterranean operations, fleet duties, and dozens of other missions. Losing half the destroyer force to coastal operations would have been catastrophic, making Atlantic convoy protection impossible and surrendering control of other theatres. But losing nearly 200 MTBs, while painful and tragic, remained sustainable because replacements arrived within weeks rather than years. The strategic calculus clearly favoured accepting MTB losses to preserve destroyers for missions only they could perform. The strategic impact became increasingly evident in channel warfare statistics as the war progressed. By mid-1943, Britain operated over 300 MTBs and motor gunboats in coastal forces. This numerical superiority transformed coastal defence from desperate improvisation to systematic coverage that left no gaps for enemy exploitation. No British convoy sailed without fast boat escorts. Every coastal route had patrols during darkness hours. Every potential E-boat approach path was watched. The numerical advantage meant British MTBs could patrol continuously while individual boats rotated through maintenance, crew training, battle damage repair. The Germans never achieved this systematic coverage despite having capable E-boats. Every E-boat sortie now encountered British MTBs waiting in ambush or responding from nearby patrol stations. The E-boats that had terrorized Channel shipping in 1940 and 1941 now found themselves hunted by flotillas they couldn't avoid through superior numbers. The predator became prey. German E-boat commanders, who had operated with relative freedom in the early war years now, faced opposition everywhere. They couldn't reliably reach British convoys without fighting through MTB patrols. When they did attack convoys, MTB escorts counterattacked immediately. German coastal traffic faced constant harassment from British MTBs operating aggressively from established patrol areas. The tonnage destroyed by MTBs accumulated steadily through thousands of small actions that individually seemed minor but collectively proved strategically significant. A German merchant vessel sunk off the Dutch coast, 3,000 tons of shipping lost. An ammunition ship torpedoed in the Channel, 4,500 tons gone plus the munitions aboard. Supply barges destroyed during cross-channel raids, 200 tons each but dozens of them sunk over months. The individual actions weren't spectacular compared to major fleet battles. No MTB ever sank a battleship or cruiser. No single MTB operation changed the course of the war, but cumulative effects proved strategically significant in ways traditional naval officers hadn't anticipated. By 1944, German coastal convoys required destroyer escorts specifically to defend against MTB attacks. German destroyers that might have been used for Atlantic operations or fleet duties were instead committed to escorting cargo vessels, moving supplies along occupied coasts. These destroyers were pulled from more important duties because plywood boats had made coastal waters too dangerous for unescorted merchant traffic. The strategic diversion was exactly what Britain needed, forcing Germany to commit major warships to defensive missions while British destroyers remained free for offensive operations. The D-Day operations in June 1944 showcased MTB versatility at operational peak. In the weeks preceding the invasion, MTB flotillas maintained continuous patrols along the French coast, preventing German E-boats from discovering the massive invasion fleet assembling in southern England. The patrols were aggressive, attacking any German vessel that ventured from harbour, forcing E-boats to remain defensive rather than conducting reconnaissance. During the actual invasion, MTBs screened the flanks of the landing force, attacked German reinforcement convoys attempting to reach Normandy beaches, and defended the beachhead from E-boat counterattacks throughout the critical first days. They performed missions ranging from torpedo attacks on enemy destroyers to mine sweeping in approach channels to rescue operations, saving sailors from sinking ships. The wooden boats proved capable of everything asked of them during the most complex amphibious operation in history. Their contribution wasn't spectacular or individually decisive, but operationally essential. Without MTB protection, German E-boats might have discovered invasion preparations or harassed supply convoys during the vulnerable build-up period. The fact that German forces were surprised by invasion timing reflected successful MTB operations denying them intelligence. The final accounting tells the complete story of this strategic innovation. British yards built approximately 400 MTBs during the war, from early 60-foot boats to later 73-foot Vosper designs, to large Fairmile D-types displacing 90 tons. Canadian yards built another 100 vessels under license, using the same construction techniques adapted to Canadian lumber resources. Total production cost approximately £12 million, roughly 6% of what an equivalent destroyer force would have required. Even assuming equivalent destroyers could have been built, which was impossible given industrial constraints, the cost savings approached £190 million that funded other essential programs. These vessels participated in over 900 documented actions by coastal forces. They destroyed around 400 enemy vessels totaling hundreds of thousands of tons of shipping. They sank 48 E-boats, eliminating the German advantage in coastal warfare that had seemed insurmountable in 1940. They damaged dozens more enemy vessels that required repair, tying up dockyard capacity. They tied down German coastal defences requiring significant resources diverted from other theatres. They enabled amphibious operations from small commando raids to the massive D-Day invasion that would have been far more dangerous without coastal control. HMS Javelin, that magnificent vessel commissioned in June 1939 at cost exceeding £500,000, suffered catastrophic damage in November 1940 when German destroyers torpedoed her, blowing off both bow and stern. Only the centre section remained afloat. Repairs consumed enormous resources and months of dockyard time, while she sat in port unable to contribute to the war effort. While undeniably valuable for missions requiring her capabilities when operational, she couldn't perform the shallow water coastal operations where MTBs excelled. Her construction cost exceeded 16 MTBs. Her construction time could have produced dozens of coastal craft. Her repair periods, when damaged, lasted longer than building multiple replacement MTBs from scratch. This comparison isn't meant to criticize Javelin or destroyers generally, which performed essential missions only they could accomplish. Rather, it illustrates fundamental differences in strategic utility for specific missions. This wasn't about replacing quality with quantity in any simplistic sense. It was recognizing that different missions required different tools optimized for specific purposes within resource constraints. The Royal Navy absolutely needed destroyers for ocean escort duties protecting Atlantic convoys that brought food and munitions from America. Destroyers were essential for surface combat against enemy destroyers and cruisers. They were critical for fleet operations supporting battleships and aircraft carriers. They provided anti-aircraft protection for task forces. They conducted shore bombardment during amphibious operations. All these missions required destroyer capabilities that MTBs couldn't provide regardless of numbers. But the Navy also needed fast, expendable coastal craft that could be risked in shallow waters without hesitation. They needed vessels that could operate in minefields, under coastal artillery fire, in waters too confined for destroyer maneuvering. They needed craft that could be built quickly using non-critical resources and lost without strategic crisis. They needed numbers sufficient to patrol continuously and establish tactical superiority through presence rather than individual capability. The 30,000-pound plywood boat filled this niche completely. The 500,000-pound steel destroyer couldn't fill this role economically regardless of superior combat power. The human cost was substantial and must be acknowledged, honestly without minimizing sacrifice. Approximately 1,400 officers and ratings of coastal forces died during the war. That casualty rate reflected the dangerous nature of fast boat operations in confined waters against well-armed opponents. These losses occurred in boats that offered no armor protection, that sank rapidly when damaged, that burned catastrophically when fuel was ignited. But those losses occurred while preventing far greater destruction of merchant shipping and the seamen aboard those vessels. Every E-boat sunk before reaching a convoy represented potentially dozens of merchant ships saved. Every German supply vessel torpedoed meant ammunition and fuel denied to Wehrmacht units opposing Allied ground forces. Every successful MTB patrol represented a favourable exchange in Britain's strategic calculation even when boats were lost. After the war, most MTBs were sold off for scrap or converted to civilian use. Their wooden hulls made them unsuitable for long-term naval service. Wood deteriorates, requires constant maintenance, lacks the structural strength for extended military operations. Many MTBs became houseboats, their engines removed and weapons stripped away, ending their days moored peacefully in marinas housing families rather than warriors. A few were preserved as museum pieces or restored by enthusiasts. MTB 102, the prototype that started everything, survived multiple changes of ownership and purposes. She was owned by the MTB 102 Trust and remains operational as a heritage vessel, participating in maritime events and Dunkirk commemorations. She sits as a reminder of when furniture makers built warships and yacht racing technology became a weapon of war. Her mahogany hull and copper rivets stand testament to an era when Britain couldn't afford perfect solutions but found adequate ones that worked. The lesson extracted from this history isn't that wooden construction was superior to steel or that cheap vessels outperformed expensive ones in absolute terms. The lesson concerns matching available resources to operational requirements within strategic constraints that limit all choices. Britain in 1940 couldn't afford to build hundreds of destroyers even if that were desirable. The industrial capacity didn't exist. The specialized materials weren't available in sufficient quantities. The skilled labor couldn't be trained fast enough. The time required made the option meaningless given immediate threats. Britain couldn't risk destroyers in coastal shallows filled with mines laid by both sides. Losing destroyers to mines or E-boat attacks would be strategically catastrophic given limited numbers and replacement times. Britain couldn't replace destroyer losses quickly when they occurred regardless of resources allocated. But Britain could build hundreds of MTBs using existing boatyard capacity that wasn't suitable for destroyer construction, small yards that would never build. Major warships could produce MTBs using familiar techniques and available materials. Britain could risk these vessels in any waters regardless of mines or enemy coastal batteries because losing individual MTBs remained manageable. Britain could replace losses within weeks, maintaining constant numerical superiority regardless of attrition rates. The strategic calculation wasn't about ideal capabilities but about achievable results within actual constraints. The calculation was brutally straightforward when analyzed objectively. Adequate weapons available immediately proved more valuable than perfect weapons arriving too late or in insufficient numbers. Britain needed coastal defense in summer 1940, not in 1942 after destroyer construction programs matured. By choosing plywood over steel, speed over armor, and quantity over individual capability, Britain gained control of coastal waters that traditional naval thinking would have surrendered as indefensible given available resources. The £30,000 MTB couldn't match a £500,000 destroyer in any single capability measured directly. It didn't need to match those capabilities. It needed to be fast enough that E-boats couldn't reliably escape, cheap enough that losses remained sustainable, and numerous enough that German coastal operations became untenable. In that specific mission, the humble plywood boat succeeded brilliantly. The motor torpedo boat program cost Britain approximately £12 million and saved the nation's coastal approaches from E-boat domination that threatened to make ports unusable and coastal waters too dangerous for commerce. Consider what that achievement meant practically. Every convoy that reached port safely delivered food that kept Britain's population fed. Every merchant ship that unloaded cargo provided materials for war production. Every tanker that survived brought fuel that kept aircraft flying and vehicles moving. The FOT, coastal war, was fought to protect these lifelines. MTBs won that war at a cost Britain could sustain. A destroyer-based coastal defence strategy would have cost over £80 million, assuming enough destroyers could be built, which was impossible given competing requirements and industrial constraints. The arithmetic alone made destroyer-based coastal defence impossible. Britain would have needed at least 100 destroyers committed full-time to coastal patrol to achieve coverage comparable to what MTB flotillas provided. 100 destroyers represented half the Royal Navy's entire destroyer strength. Those destroyers were essential elsewhere. Atlantic convoys required destroyer escorts. Mediterranean operations demanded destroyer support. Fleet duties absorbed dozens of destroyers. Diverting 100 destroyers to coastal patrol would have meant abandoning Atlantic convoy protection or Mediterranean operations. Either choice would have been strategically catastrophic. Even if constructed, destroyer-based defense would have been operationally inadequate because destroyer numbers would remain insufficient for continuous coverage. Destroyers required more maintenance time than MTBs. Their complex machinery demanded regular dockyard work. Their larger crews needed shore leave and training. Each destroyer would spend substantial time unavailable for operations. To maintain continuous patrol coverage, Britain would have needed perhaps 150 destroyers, accounting for maintenance rotations, crew training, battle damage repairs. Building 150 destroyers would have consumed virtually all British shipyard capacity for years while diverting resources from every other program. The strategic opportunity cost would have been unacceptable even if physically possible. That £68 million difference between actual MTB costs and hypothetical destroyer costs funded other operations and procurement programs across the war effort. £68 million in 1940 currency represented enormous purchasing power for military equipment. Aircraft production benefited from resources not consumed building unnecessary destroyers. Bomber Command expanded its heavy bomber fleet. Fighter Command maintained strength necessary for defense. Coastal Command received patrol aircraft for anti-submarine operations. Tank manufacturing expanded using industrial capacity and materials that remained available. British tank production increased steadily through the war, providing equipment for armoured divisions fighting in Africa, Italy and France. Submarine construction proceeded without competing for materials or dockyard space needed for destroyer building. British submarines operated successfully against enemy shipping throughout the war. Merchant ship construction continued at maximum possible pace, replacing losses and expanding carrying capacity. Liberty ships and other cargo vessels were built in Dawes in Enter, British yards supplementing massive American production. Naval base construction provided facilities supporting operations worldwide. Port improvements expedited cargo handling. Training facilities expanded to handle growing numbers of sailors, soldiers, and airmen. All these programs contributed to victory using resources that weren't diverted to unnecessary destroyer construction for coastal defense. The MTB program demonstrated something fundamental about modern warfare that remains relevant today. Technology and industrial capacity matter enormously in determining military outcomes, but matching technology to missions matters equally. Having the most advanced weapons means nothing if you cannot afford them in numbers needed or deploy them where required. Having adequate weapons available immediately often proves more valuable than perfect weapons arriving later. Understanding these relationships, thinking creatively about how to achieve necessary outcomes within real constraints, often determines success or failure more than raw technological superiority. British planners in 1940 faced catastrophic constraints. France had fallen. Germany controlled the Channel coast. E-boats were sinking ships within sight of English beaches. Traditional solutions weren't available. Britain couldn't build enough destroyers fast enough. Resources were desperately limited. Industrial capacity was fully committed. Time was critical because losses were mounting daily. Creative thinking was essential. The MTB program represented that creative thinking at its best. Take existing technology from civilian applications. Adapt it for military use with minimum modification. Build using available resources and existing facilities. Deploy in numbers that create strategic effect through quantity rather than individual quality. This approach offended traditional naval thinking that prized individual ship quality above everything. The Royal Navy had dominated oceans for centuries, through superior ships crewed by professional sailors. The idea of deliberately building fragile vessels that couldn't survive combat went against every instinct. But war forced adaptation. The choice wasn't between perfect solutions and adequate ones. The choice was between adequate solutions available immediately and perfect solutions that would arrive too late to matter. MTBs were available immediately. They could be built starting instantly. They used available resources. They worked. The principle extends beyond naval warfare or even military applications. Any organization facing resource constraints and urgent requirements must make similar calculations. Do you pursue ideal solutions that exhaust resources and arrive late? Or do you accept adequate solutions that work within constraints and deliver results when needed? Neither approach is universally correct. The answer depends on specific circumstances, available resources, time pressures, consequences of delay. But understanding the question matters. Recognizing when adequate and available beats perfect but delayed represents strategic wisdom that MTBs embodied. Sometimes the best weapon for a specific situation isn't the most powerful option available or the most sophisticated technology a nation can produce. Sometimes the best weapon is simply the one you can afford to build in the numbers required when you need them, using resources actually available rather than resources you wish you possessed. The British wooden MTB embodied this principle perfectly, demonstrating that strategic success often comes from realistic assessment of constraints and creative solutions that work within those limits, rather than pursuit of ideal solutions that exceed practical capabilities or arrive too late to matter. Britain won the coastal war not through superior technology or overwhelming resources, but through creative thinking that matched available means to necessary ends.